Okay, it's 3 o'clock, so let's go and get started. All right, good afternoon, everyone. Welcome to the last class session for EGME 410 for the summer. How's everyone doing today? Good, good. Okay, so today's just a miscellaneous day, so just kind of what we promised. And so, if you have questions on your project, we're more than happy to answer all your questions. But looks like everyone that's here was just in office hours just an hour ago. So, unless something changed over the last 30 minutes, then probably won't be too much to discuss. But I did want to make everyone aware of all the handouts that I posted today. So over the years teaching this class, there's always been interest in certain kind of more niche features within ANSYS. So these features are a little bit too niche to include kind of in the regularly scheduled programming. And a lot of them are kind of too small to make a full activity for it anyway as well. But they do represent important features within ANSYS to do certain things that are very useful in some situations. So I've made handouts for them all. So if you go to the weekly page, if you go to the Canvas site here, you go to week 5, part 3, you'll see that there are 8 handouts here on kind of more miscellaneous stuff that I've made over the years for ANSYS, although I don't think I've made anything new in the most recent years. So these have topics from things like optimization, buckling analysis, anisotropic materials, fatigue life analysis, thermal analysis, creation of force surfaces, fluids, and harmonic response. So I even completely forgot that I made a handout on harmonic response yesterday. So yesterday I was just kind of trying to wing it, but I already have a handout for it here. So this is probably more detailed in terms of what to expect for that. So all that is available for you guys, and so obviously we won't have time to cover all of these in class, but I did want to make you aware of their existence. All right, so for today, what I thought I would do is I would go over a couple of these that people have asked me about this for this summer, just so that we kind of go through it together. So I did want to do the thermal analysis together, just to kind of give you guys an idea that ANSYS can do things other than structural analysis. So we'll go over this together. We'll do a very basic thermal simulation, and then I also wanted to do fatigue life analysis as well. So we'll do both of these together. I don't think they'll take very long. For the thermal analysis, there's a little bit of a lecture that goes along with it, just to introduce those concepts. But these shouldn't take more than an hour between them, combined. So we'll go over both of those together, and then for the rest of class, probably from 4 until 5:50, I will let you guys just kind of ask questions about your project. Okay. All right, so that's the plan for today. Any questions about the project or anything? Oh, I've graded your midterms, and so you should be able to see your grades for that on Canvas. So I do have them in person, and so if you somehow want to come here and pick up your exam, I'll be here until 5:50 today. Today is the last day that I'm planning to be here on campus for the summer. I will be back here for the fall, and so if you wanted to come by my office during the fall and pick up your exam, then you're welcome to do that as well. If you're ever curious, I always prefer students to come pick up their exams, because otherwise they just end up cluttering my office. If you've been to my office, you've probably seen just exams from all the past years all over the room. So if you can pick up your exam, that'd be great. Otherwise, I'm just going to be trashed maybe 4 or 5 years from now. Average, I think you should be able to see on Canvas as well. I actually forgot to compute it, but I think Canvas kind of shows up for you as well. Just because I've had a few questions about this as well. I do curve my classes, but I don't curve until the very end of the course. And so what I typically do is that once all the final grades are in, so basically once I grade your final projects, I'll go into the grade book and I'll look at the overall class average. And if the overall class average is below, probably 80, 81, 82%, kind of depends on kind of where things are. Then what I'll do is I'll add points to everyone's grade until it reaches that threshold. So for a technical elective like this, you guys didn't have to choose this class. You guys chose it because you wanted to learn it. Usually I'm a little bit more lenient with curve than my other classes. So I'll try to aim for a class average of around, probably a low 80s. And so 80, 81, 82%. Traditionally in this class, I've never had to actually apply a curve just because people tend to do pretty well on the projects. This summer is a little bit different just because it is pretty accelerated, and so So I don't know what the curve would be, but you can probably expect maybe at least a couple points to be added to your grade by the end. But if everyone does really well on their final project, then there might not be need for it at all either. Okay. All right, so that's the grading policy. So I'll do that automatically, and so when all the final project grades are in, and you kind of see your final score on Canvas, that's that. I'm not going to read that exactly for the final grade unless the average is already above 80%. And so your final letter grade may not correspond to your Canvas grade, but it's not going to be worse than your Canvas. I've never subtracted points from people. I think that's just rude in the usual. Okay, any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. So if you're in the room, so the midterm exams are up there, so you can feel free to pick it up at any time. Let's go ahead and get started. Okay, so first thing I wanted to go over together with everyone today is thermal analysis. And so, we've focused everything on this class on structures, but, finite elements is capable of so much more. And so as long as your phenomenon or physics is governed by a differential equation, finite elements is able to solve that. And that goes beyond, so I had a conversation with someone in office hours today. Finite elements or the capabilities of finite elements goes even beyond what's here in ANSYS. Although I would say ANSYS does a pretty good job of being fairly comprehensive, at least among the basics of all these different fields here. But you can see that there's quite a variety of different types of phenomena that you can simulate. And so there's thermal simulations, structural simulations, modal fluids, lots of different fluids simulations, dynamic simulations. All that stuff is there. Okay. So I did want to go over thermal, just because that's thermal. I would say is probably usually the second step after you do structural simulations. Is thermal is kind of a nice one to set up. Okay. So if you've already taken the heat transfer class, this will be a lot of this will be kind of review. If you haven't taken heat transfer yet, then you can look forward to taking some of this upcoming year. But just know that it's we're just going to go over just the basics that you. All right. So the main thing to know with a thermal simulation is that we are going to be solving what's known as the heat equation. So the heat equation is given by this one here, or this is one form of the heat equation. It's basically the second order derivative of temperature with respect to each of the Cartesian directions. So partial squared t partial x squared plus partial squared t partial y squared plus partial squared t partial z squared plus q dot, which is a thermal forcing and or thermal generation, and is equal to F, which is a thermal forcing. Okay. So what ANSYS is going to be doing is it's going to be solving this equation internally for the temperature distribution in your geometry. Okay. So what we're going to go over here is just the basics in terms of how to set up such a simulation. Okay. Okay. So just like our structural simulations, we're going to start with geometry, connections, meshing. The good news is that none of this really changes. And so, no matter how you set up no matter whether you're doing structures or thermal, your geometry and meshing, those details are going to be the same, right? The only difference being is that for a thermal simulation, it's not as strict on the element order. You can use a linear element, and usually it doesn't really impact your solution all that much. But even then, quadratic still does help. And so, all the basics and all the understanding that you know about meshing in a structural sense can be applied here for thermal simulations as well. Okay. Okay. So where things do get different is basically with the material properties and the boundary conditions. Okay. So I did want to talk about the boundary conditions first. Okay. So all of the structural boundary conditions that we've used so far, so things like fixed supports, forces, pressures, all of that kind of goes out the window because those don't really have any bearing on the thermal response. Okay. So when we think about boundary conditions in a thermal simulation, you're thinking about boundary conditions on the temperature, basically. Okay. And that's kind of the main difference is that instead of solving for the deformation as you would in a structural simulation, you're instead solving for temperature. And basically all your boundary conditions are just anything that can influence the heat or temperature of your geometry. Okay. Okay. So we still have kind of this concept of constraints and loads. It's just that, what constitutes a constraint and what constitutes a load for a thermal simulation are different. Okay. So for constraints, right? If you think about how we did constraints in a structural simulation, a constraint was a direct kind of specification of the deformation at a certain part of the geometry. Okay. Now, for a thermal simulation, what is considered a constraint is a temperature boundary condition. Okay. So anytime you specify the temperature of your geometry at a very specific location, that is considered a constraint. Okay. Okay, so for instance, here in this diagram here, we're specifying this face of this cylinder here to be 100 degrees C. I know it's a little bit hard to see if you're on, especially if you're on Zoom. But because we are requiring that every node on this surface here is 100 degrees Celsius, this constitutes as a thermal constraint. Okay. Okay. Now for the loads. And so the loads for a thermal simulation have to do with the transfer of energy. Okay. Specifically thermal energy. And so heat flow is basically an input of heat into a system. So think of, maybe putting your geometry onto a stove, right? So as you put your geometry onto a stove, right, it's absorbing energy in the form of heat from the stove. That is what I would consider like a heat flux or a heat flow type boundary condition. Okay. So that would be a load for our case. Okay. A special type of load type boundary condition you can have is what's called a perfectly insulated condition. So if you think of insulation, right? So when we think of insulation as engineers, insulation has to do with the blockage of heat, right? And so when you want something to kind of retain heat, you try to insulate the outsides. So one common application is that, let's say that you're designing pipes, that are going to be going through a residential section in a very cold area. Usually you want to apply insulation. Otherwise, any hot water that goes through a pipe that goes outside, all that heat is going to be lost. Okay. So we can apply a perfectly insulated boundary condition to prevent any kind of heat loss or any kind of heat entering to a geometry at a certain location. Okay. So for instance, for this diagram here, we've specified this space. I know it looks similar to this one, but this is you can consider this as the other end of that cylinder. We've specified this as perfectly insulated, so no heat can enter or leave the geometry from this face right here. Okay. Okay. The next type of boundary condition we can have is convection. So this is kind of a unique one. So convection, if you've taken heat transfer before, you probably know what convection is. But if you haven't taken heat transfer, convection is basically the transfer of heat to some kind of moving fluid, right? So if you have air that's going over an object, then that airflow is going to enhance the heat transfer that comes out, right? That's why you feel colder whenever there's wind chill. So when there's wind chill, it's not necessarily that the temperature is dropping with wind chill. It's just that when you have wind that's blowing across your body, more heat is able to leave more quickly because of the convection effect. Okay. And so we can apply this as a boundary condition in ANSYS as well. And so the main equation to worry about with convection is this one right here. Okay. Where Q here is the convection heat loss, right? And so you can see the convection heat loss is dependent on the difference in temperature, right? So Ts is the temperature of the surface, T infinity is the temperature of the fluid. That is multiplied by A, which is the surface area of the object, and H, which is what we call the convection coefficient. Okay. Now, the tricky thing about convection is that, solving for H or determining what H is for a practical sense is usually pretty difficult. And so, that's what kind of makes things tricky to apply in finite elements as well, because we have to come up with some value for H. And H is dependent not only on the fluid, but it also depends on the fluid velocity. It depends on the fluid flow conditions, the flow patterns, temperature, things like that. And so typically for H here, the way that it's found is that usually we run a fluid simulation as well to determine H. But this is something that you have to kind of think about applying for a convection boundary. Okay, I am going pretty fast here just because I do want to leave time for people to ask questions about their projects, but I did want to kind of just introduce everything. Okay, another type of boundary condition you can have is a radiation type boundary condition. So radiation is basically the transfer of heat via electromagnetic waves. It's a very unique form of heat transfer because most other forms of heat transfer require some kind of medium, either like a solid or a fluid for the energy to transfer through. Radiation doesn't require that. In fact, radiation is the primary means by which the Earth's heat reaches the Earth, or the sun's heat reaches the Earth, because there's no matter in space, and so there's no sense of conduction or convection in space. Okay. Now, usually for most cases, radiation is going to be pretty negligible for any surface that's on Earth, just because of for most heat transfer on Earth, heat transfer is dominated by conduction or convection. But radiation is something that you can apply in ANSYS as well. Okay, there are quite a few parameters that you have to specify for radiation. One of them being the emissivity of the surface, and theta and sigma here is what's called the Stefan-Boltzmann constant. Okay. But so just kind of be aware of that. But most of the time, unless you're designing something that's going to have space applications, most of the time you're not going to require or have radiation be of significant value in your simulation. Okay, another thing that you can do for your thermal simulations is that you can have what's called internal heat generation. And so if your material is able to generate heat or absorb heat, then you can incorporate that as well. This is pretty rare, I would say. Most materials are pretty benign in that they're not going to be producing heat. It's only if you were simulating, let's say, like a cold pack or like a heat pack, where that there's some kind of chemical reaction taking place that's generating heat. Most of the time, you're not going to consider internal heat generation. But the capability is there within ANSYS if you do have that kind of niche scenario. Okay. Okay. And so that's all the boundary conditions. And just like in a structural simulation, we have to specify the outlets as well, outputs. And so from a thermal simulation, you can output temperature. So that's basically just the temperature distribution within your geometry. You can output heat flux. Okay, so that's the amount of heat that's leaving or entering your geometry. Okay, and you can go from. Okay, so to demonstrate, I have this kind of very simple simulation. We've kind of already been setting it up. Okay, so we have just a simple cylinder here. It has a diameter of 5 centimeters, a length of 100 centimeters. We are going to consider some radiation just to kind of demonstrate for you, and there's going to be some convection as well. Okay, so we'll set this up together in ANSYS just so that you can kind of see how it's set up. And there's a lot more details in the handout here for you to look at as well. Okay. All right, questions? Yes.
I wanted to ask, so this is kind of like not exactly related to it, but when we're working with, just say like fatigue or static structural, but we do want to incorporate like an operating temperature.
Mm-hmm.
There might be some flux and some, but it's minimal. But the idea is like it's really hot, like part that you're simulating. How do you is that just like a simple setting in ANSYS kind of a thing?
So if the part is going to be at a constant temperature, you can specify that within just static structural. So a lot of times from a structural point of view, usually the only reason you care about temperature is that it's going to affect your material properties. And so your stiffness, your density is going to change on temperature. Now your material model has to account for that. And not a lot of materials in ANSYS can account for that. I think structural steel may be the only one that can do that. And so you can input that manually. And so if you do have data from like a material data sheet in terms of how like the Young's modulus or the density changes with temperature, you can input it manually. But there is a way to do that in static structural. We can say that the temperature is going to be this. Now I haven't played around with it too much, but I've only just kind of seen the feature. But I know that it exists just for that purpose. If you're going to have significant temperature variations where one section of your parts will be much hotter than the other one, you may have to couple the simulation. So you may run like a thermal simulation and couple that together with the structural, so that point by point it can compute the temperature and then kind of more dynamically compute what the material property is going to be based on that temperature. So there's a way to do that as well. It shouldn't be too expensive because both structures and thermal are fairly cheap simulations. It's not like fluids. And so, it shouldn't be too hard to set up. And so you'd probably set it up the same way as we did yesterday with the modal simulation. You would just take one and just kind of drop it on the other just so that they kind of share solution information. Okay. I would probably do thermal first, just because the thermal, it's usually a one-way street. The structural response is not going to affect the thermal response, but the thermal response is going to affect the structures. And so I would run thermal first and then drop the static structure on top of that, just so it can share that coupling that way. All right, any other questions? Okay, all right, so let's do a quick demonstration. I don't want to spend too much time because I do want to get to fatigue life today. But let's do there you go, steady state thermal. Okay, so for thermal simulation, there's two versions that you can do. You can either do a steady state version or a transient version. Okay. And actually, to save time, let me do this. Let me just import a part that we've done before. So let me actually import let's import the crank. So this is back to activity 2. The crank is actually just a very nice geometry to use. Okay, and then let's go ahead and open up ANSYS mechanical from. So the nice thing about thermal simulation is that the interface is actually exactly the same. So ANSYS mechanical, even though it's called mechanical, mechanical there stands for mechanical engineering. That's how I think about it. So you can do the thermal simulation straight from that same interface. It's a little bit different for fluids. And so if you want to run fluids, there's a separate program for it called Fluent. I do have a handout for that that's available online as well. That's A7. But the reason we're not doing it in class is because it's a 20-page handout. There's a lot to explain for fluids. And so, but if you were interested in fluids, there is a handout for you there. Okay. All right. So we have our bike crank here, right? So let me go ahead and let's suppress the same parts as we did before. Okay, so let's go ahead and generate a mesh. And so, for this mesh, we don't really need anything too crazy for it. Let's say that our mesh size is going to be, let's do 5 millimeters. Okay. It's a little bit too coarse. Let's go to 2.5. Okay. All right. So that's perfectly fine. Okay. So let's demonstrate how to set up a thermal simulation. Okay. All right. So even though it's not exactly what the example is here, I think it's close enough to a cylinder. Okay. So if you look at our example here, we have a fixed temperature boundary condition on one side, an insulated boundary condition on the other side, and then we also have convection that's going across the outside as well as radiation. Okay, so we have basically 4 boundary conditions that we need to specify. Okay, so let's go ahead and specify those conditions here. Okay. Okay, so first let's specify the fixed temperature boundary condition. Okay. Okay, so let's specify this region right here as having a fixed temperature. Okay, we're kind of lucky in the sense that this geometry here lets us select just this side of the bar. It's not always like this. Sometimes you would only be able to select the entire exterior. Okay, so to apply a thermal boundary condition, you're going to do it the same way. So you're going to right click on steady state thermal, go to insert, and then go to temperature here. Okay. All right, so just like we did in the structural sense, we need to specify which parts of the geometry that we want to specify this temperature boundary condition on. Okay, so let's go ahead and set that one there. And let's set this to be 100 degrees C. So the nice thing about thermal simulations is that temperature is a scalar quantity. Deformation was a vector quantity. And so remember, we usually had to specify the X, Y, and Z components of deformation separately or forces separately. But for temperature, there's only one dimension, just because there's only one temperature. Okay. Okay. So that right there acts as our constraint. And so actually, if you remember from our discussion on boundary condition, right? Well, remember what we talked about, that every finite element simulation has to have at least one constraint. And so that idea translates to thermal simulations as well. It's just that instead of being a constraint on the deformation, for thermal simulations, our constraint is on the temperature. Okay. Okay, so we're specifying a temperature constraint on this end here. And then on this other end, we're going to have a insulated boundary condition. So let's go ahead and insert that. So we're going to insert perfectly insulated. And then let's click on this end right there. Okay. Okay, and so if you look at the details for the perfectly insulated boundary condition, you can see that This is set at 0 watts. And so what that means is that 0 watts of energy or power are able to leave the geometry from this region right here. Okay. Okay. All right. So technically, that's all we need. So we have basically one constraint and one load, and so we can actually run the simulation here, and let's see what that looks like. Okay. All right. So I'm going to set the boundary conditions to be temperature and total heat flux. So let's go ahead and solve. Okay. Right, so basically it's going to solve for the temperature distribution in this bike crank here, okay? Where we set a temperature of 100 degrees C on the left and an insulated boundary condition on the right. First simulation of the day always takes a while. Okay. Okay. All right, so what do we see here? So you can see here that the entire structure is ballooned, right? So that looks strange, right? And you can see here that the entire structure is set to 100 degrees Celsius, right? So how can that be, right? How can our entire structure here be the same temperature? Well, let's look at our boundary conditions again. So we set that this region of the geometry has to have 100 degrees Celsius, right? So we know for sure that this region right here is 100 degrees Celsius, okay? What we also said was that this region right here is perfectly insulated, so no heat can leave this geometry from this region. But what about everything else, right? We haven't specified boundary conditions on any other region of our geometry here, right? Now, if you remember from our discussion of boundary conditions, right, what we said was that, even if we don't specify it, every exterior surface has to have some boundary condition assigned to it just because they're on a boundary, right? And whenever we don't assign a boundary condition to a surface, ANSYS is going to assign a default boundary condition, okay? Now, for a structural simulation, the default boundary condition was a stress-free boundary condition. So essentially, there's no load applied to it, right? And that intuitively makes sense. And in fact, we've never actually thought twice about it. But for a thermal simulation, the default boundary condition is actually quite interesting. So the default boundary condition for a thermal simulation is actually a perfectly insulated boundary condition. And so what we've done by default here is that we've assumed that this entire bike crank here is perfectly insulated. And so no heat can enter and no heat can leave. And so this temperature of 100 that we're specifying here, because no heat can leave, right? In order for this structure to be at perfect thermal equilibrium, the entire structure must be at the same temperature then, because no heat can enter or leave, right? And the only way that's possible is if the entire structure was at the same temperature, okay? So you have to be a little bit more intentional with your thermal simulations, and that you have to make sure you apply a boundary condition on every surface, unless it's a perfectly insulated case, right? But that's very rare. It's very rare for an entire structure to be perfectly insulated everywhere, okay? Okay, so let's make this a bit more realistic. And so let's go ahead and add our two other boundary conditions here. So let's add our convection boundary condition and let's add our radiation here, okay? Okay, so let's add our convection boundary condition. Okay, so just same way we did before. So we're right click on steady state thermal, go to insert, go to convection, okay? Let's select all the exterior surfaces here. So that's the two lateral sides as well as the top and bottom, okay? I know we didn't specify the internal holes here, but that's fine. Okay, so now what we're saying is that the entire exterior surface of the bike crank, with the exception of our temperature boundary condition and our insulation, there's going to be airflow or some kind of fluid flow that's going to be extracting heat from the part. Okay. Okay. Now, when you specify a convection boundary condition, there are two parameters that you have to set. So one of them being the convection coefficient, and the other being the ambient temperature, okay? Now, ANSYS calls the convection coefficient the film coefficient, but that's, it's just terminology. They mean the same, okay? Okay, so let's go ahead and specify our convection coefficient here, which is 0.5 watts per meter squared Kelvin, okay? Be careful of the units, right? And so right now, this is in watts per millimeter squared degrees Celsius, right? So let's go ahead and switch to meters. Celsius and Kelvin are interchangeable. They mean the same thing in terms of units. Okay. All right, so now that we've set our units to meters, we can now set our convection coefficient to 0.5. Okay. And our ambient temperature is just the temperature of the air around the part. So for that, we're going to specify 25 degrees C to match with our efficiency. Okay. Okay, so now we've added convection. So now heat can leave the bike crank via airflow around it, right? So that helps us out a lot. And let's also add radiation as well. Okay, so same thing for radiation. We need to specify all of the surfaces where heat is going to be radiating from. Okay, so let's select all of the exterior surfaces just like we did before. Okay. Okay. And just like the previous step, we need to set the ambient temperature. So let's set the ambient temperature to 25. And then for the emissivity, right? Emissivity is a property that describes how well the surface can emit heat. So it varies between 0 and 1. It's actually a ratio. So usually for a practical surface like this, emissivity of around 0.3 is pretty common. So let's go ahead and put that. Okay, all right. So now we are enabling heat loss via convection and radiation. So let's go ahead and run the simulation again. And you will see that the results are going to change quite a bit. Okay. All right, so this looks a lot more reasonable here. And so you can see now we actually have a temperature distribution, right? And so temperature is maxing out at 100 degrees Celsius here on where we applied the temperature boundary condition. And then now we actually have a gradient. And so temperature now drops from 100 on one side to about 83 degrees Celsius on the other side, okay? And we can see where most of the heat is being lost as well. So you can see that there's more heat loss around this region, kind of where the temperature boundary condition is, okay? Okay, so that's just a very, very brief introduction to the thermal simulation. I know we kind of went through that at 100 miles an hour, but the main thing to remember is that, just remember, you have to have at least one temperature boundary condition in your simulation. And remember, you have to be very intentional in terms of how you specify the boundary conditions. Because if you don't, then you kind of end up with what we had before, where every surface is insulated and we have no basically any heat loss from the system or heat gain, right? Sometimes you may have your part being heat. Okay. All right, any questions on thermal simulations and how we set this up? Okay, perfect. All right, and we are perfectly on schedule too. Okay, so that's thermal simulations, right? And so if you are interested in running that for your final project, there is the handout for that. Okay, so it's handout A5. So since a few people just kind of joined in, bless you. I did want to let you know that I've written handouts for a lot of kind of more niche and kind of specialized features within ANSYS. These are features of ANSYS that we didn't really have time to kind of go over in the regular class. But people are usually interested in them for one reason or another. Usually for maybe their senior design project or maybe a personal project. And so I made handouts for all of these. So those are all available to you on the Canvas site. And so if you go to week 5, part 3, you go to the weekly page for that. So you go to the home page, you go to week 5, part 3, right? So here's all the handouts. And so what we just did was we did handout A5 for thermal analysis, just because I know a few of you guys are interested in doing that for your final project. So that is kind of the basics for that. The other one I wanted to go over today, just because there's been interest from it in the class, is fatigue life analysis. Okay, so fatigue life analysis is a very interesting type of analysis you can do in ANSYS. Basically, you can predict, whether your part is going to have fatigue failure or not. Okay, so this is a very useful tool because when you're designing a part and your part is designed to kind of undergo lots of different loading cycles over its lifetime, right? What tends to occur is that the material in your part is going to actually fatigue, and so its strength is going to actually get reduced as you apply more and more loads to it, more and more cycles of load. Okay, and so what can happen is that your part can actually fail without it actually reaching the ultimate yield strength of the material. Okay, so ANSYS gives you a way to estimate it. I wouldn't say it's a perfect method, but it should give you kind of a ballpark estimate in terms of whether your part is going to fail or not in fatigue. Okay. Okay. All right, so let's go ahead and get into that analysis here. Okay. Okay, so let's go back to Workbench here and let's go ahead and just start a new project. Okay. Okay. All right, let's see. Okay, so to do a fatigue life analysis, the nice thing is that you can do it straight from a static structural analysis here. Okay, so let's go ahead and load in static structural. And let's go ahead and import a geometry. And so just for the sake of brevity here, let's go ahead and load in our crank assembly. Okay. Now, before we jump into ANSYS mechanical, we do have to talk about the material properties. Okay. Now, to do a proper fatigue life analysis, your material has to be basically set up for it. Okay. So what do I mean by that? So let's double click on engineering data. Okay. And let's look at structural steel. Okay. Okay. So to do fatigue life analysis, you have to have the fatigue data for that particular material. Okay. So for structural steel, ANSYS is actually pretty nice. It actually has it already built in. And so in order to do a fatigue life, you have to have what's called the SN curve. Okay. Now, but for structural steel, this is built in automatically. But for other materials, you may have to add this in manually if it's not already built in. Okay. So let's look at this SN curve and let's see what information is here. Okay. Okay. So if you click on this SN curve, you can see that we have this new table here. Okay. And so this table is kind of everything that you need here. And so basically what this table tells you is that based on the number of cycles, okay. So the cycles here being the number of loading cycles that your material is going to be part of, right? So one loading cycle is defined as, basically applying the load and then relaxing. Okay, so one cycle of that. So application of load, relaxing it, or maybe even reversing direction. That's one cycle. Okay. All right, and then based on that, then the other column of this table here tells you the maximum amount of alternating stress that the material can withstand. Okay. Okay, and so what you're seeing here is that as you load the part for more and more cycles, the maximum amount of alternating stress actually starts to go down. Okay, because what tends to happen is that as you load your material over and over again, you actually start to weaken, some of the molecular bonds within the material itself, and so it's susceptible for failure a lot more easily. Okay, and so your SN curve, or basically the number or the strength based on the number of cycles, goes down as the number of cycles goes up. Okay. Okay, so in order to do a fatigue life analysis, you have to have this information for your material. Okay. And just be aware that, if you're adding another material, so let's say that, well, first of all, if you create a material from scratch, you have to kind of do that yourself. But even if you're using a material within ANSYS itself, so let's look at aluminum alloy. Okay, so that's one that we've used a lot before. Okay. Oh, actually, aluminum alloy, this is probably new. So aluminum alloy also has an SN curve as well. So this is actually pretty nice. And so, if you want to do a fatigue analysis and your material is part of this library, let's check another one, actually. Let's check a few. Let's see if they all have an SN curve. So let's look at cast iron and let's look at concrete. So actually, concrete is a very common material that you want to test for fatigue for because, a lot of, bridges and stuff are made of concrete. Okay, so unfortunately, it looks like concrete does not have the fatigue data. A little bit unfortunate. Concrete is usually a very prime candidate for fatigue analysis. Same thing for cast iron. Okay, so it looks like some materials in ANSYS they do have that SN curve, but not all of them. Okay, so that's one thing you want to check. If you do want to run fatigue analysis, check and make sure that your material has it. So if it doesn't have that SN curve, you're not going to be able to run fatigue life analysis. Okay. Okay. All right. So let's go ahead and jump into ANSYS here. Or let's jump into ANSYS mechanical.
So if we wanted to do, if we were working on a bridge and we wanted to do the fatigue life on it, is there a way to add in like that kind of sort of thing?
Yes, and so yeah, so it's basically one of the custom material properties that you can add in. And so once it loads, I'll show you. But on the left, so you click on a material, there's a menu there for fatigue properties, and so you basically click and drag SN curve. You just have to input in manually. And so, so sometimes that data is published for a material data sheet, so you can just input it from there. And sometimes you might find it in the literature as well. People have done material testing. Yeah. Oh, yeah. Okay, let me show you the engineering data first. It looks like the simulation did not load. Okay. All right. So if you want to add like an SN curve here, so let's say we want to add it for concrete. Okay. So you go under here. I think it's under life. Yeah. And so you go to life here, and then you go to SN curve. You click and drag it onto there, and then you can input that. You can input that here. And so basically, it just gives you a blank table, and you just input number of cycles and the alternate you specify. Yeah. Let me go ahead and okay. All right, let's come back here. Yes. Okay. All right. So we have our part here once again. Okay. Got a little bit disorganized here. Let me go ahead and open up the handle here. Okay, so we opened up our part here. So the nice thing is that, for the most part, we can set this up pretty similarly to a static structural analysis. Okay. So let me go ahead and suppress these just because we've done. Okay, so let's go ahead and generate a mesh again. And so let's go ahead and change this to millimeters here. So let's set this to be 2.5 millimeters for the mesh. Let's go ahead and generate that mesh pretty quickly there. Okay. All right, so that looks good. Let's go ahead and apply the loads here. So let's go ahead and specify a fixed support. Just like we did in activity 2, we're going to specify these holes as the fixed support. Okay. Let's apply a force load. And so let's apply a force load on the inner part of the pedal here. Okay. Okay. And just like before, let's switch this to components. And let's set the load in the Y direction, and let's set it in pounds, just like we did that. Okay, 100 pounds going in the positive Y direction. Okay, good. All right, so let's go ahead and add in our total deformation and our equivalent stress. Okay. Okay. All right. So to do fatigue life analysis, we need to load in the fatigue tool. Okay. Okay. So you're going to load the fatigue tool, you're going to right click on solution A6. You're going to go to insert. Okay. And you're going to see here that there is a menu here for fatigue. Okay. And so from fatigue, you can add this fatigue tool. Okay. So let's go ahead and add that in. All right. And so this is where you can specify your fatigue parameters here. Okay. Okay. All right. So let's go ahead and specify some parameters here. Okay. All right, so the first thing we have to do is we have to specify the condition on the loading here. Okay. Now, remember when we're talking about fatigue life, we're talking about different load cycles, right? And so we want to see how many load cycles that our part can withstand before it can fail, right? So the first thing we have to define here is what constitutes as a cycle, right? So by default, the loading type is set to fully reversed. And so what that means is that when we have our load here, right? So our load right now is going in the positive Y direction. And so fully reversed, what that means is that in order for a load cycle to complete, we're going to specify 100 pounds in one direction, then we're going to gradually change it to the other direction, okay? And so as the force line goes up and then back to neutral, that's one cycle, okay? So that's called a fully reversed loading cycle. And so so in that case, the loading direction actually changes direction. Another way you can do the loading cycle is you can do zero-based. Okay. Right. So this is actually more common where, in a zero-based loading scenario, the load will go up to its maximum value of 100 and then go back down to 0. Okay. It's not going to change direction. And so on the zero base, it just goes up and then back, up and then back. Okay. So you can choose which one of these that you want given your situation. Okay, and what you pick, it depends on your situation there. Okay. For a bike crank here, I'm actually going to pick fully reversed because this bike crank can, it's going to be experiencing loads in this direction as well as this direction, depending on the position of the bike crank. Although, this situation for the bike crank is still a little bit contrived because we're applying fixed supports here. Okay. Okay, so we do have to specify that. Okay, you can also amplify the load as well. Okay. Okay. All right, and so the other thing that we have to specify here is your mean stress theory. Okay. Okay. So this will take a while to explain, and honestly, I don't know if I have the technical background to really give a good explanation of what this is. But basically, this is the theory. This is kind of the fatigue theory that goes into determining how many cycles that your part can withstand based on the loading and based on the SN curve for your model, right? So there's a bunch of equations that go into this, but basically you need to choose one of these ones here, okay? Okay, so the two most common ones are, the most common one I would say are the Soderberg and the Goodman theory, okay? All right, so the Goodman theory you can see goes like this. And so basically your material is going to be good up until here, and then its strength is going to steadily decrease until you reach the ultimate yield strength, okay? The other one is the Soderberg, which only goes up to yielding, okay? So you can determine which one is kind of more appropriate for your case. And so we're either going to go to ultimate material failure or just material yielding, okay? So for this case, let's just go up to yielding. Okay, and then the other things that we can add here is let's go ahead and add some outputs. And so let's add life, and then let's add safety factor, okay? Just so that we can view the results of the fatigue tool, okay? So life is going to tell us how many cycles the part can withstand at different sections. And safety factor is kind of more self-explanatory, just a factor of safety in terms of how we can use that for our design. Okay, they kind of show the same information, just kind of in slightly different ways. So we're running our simulation. It first has to run the static structural simulation, and then based on that, it runs the fatigue tool. So it is slightly more costly, although not that much. Okay. Okay. All right. So let's look at life first. Okay. So you can see here that everything in blue can survive up to 1 × 10⁶, which is a million cycles. Okay. So based on our 100 pounds loading here, right? The majority of this bike crank is able to survive for up to 1 million cycles, okay? But you can see that there are sections of this bike crank that will fail before 1 million cycles, okay? Right, in particular, right at the neck here, which is the thinnest part of the bike crank, which theoretically makes sense, that's the weakest part. This is only able to survive for about 690,000 cycles, okay? Right, and so this part of the bike crank is going to fatigue and fail first. Okay, it's going to fatigue, after 690 cycles. Okay. All right, next we can look at the safety factor. So safety factor kind of gives you a sense of which sections of your material or which sections of your geometry are more likely to fail than others. Okay, so you can see here with safety factor analysis that the area around the neck is highlighted in red, right, and so that gives us a safety factor of 0, right. So safety factor 0 in this case means that it's going to fail before it reaches the 1 million cycles, okay? But even beyond that, you can see that there are other parts of this geometry here that are at danger of failing just because their safety factors are lower than the maximum of 15 here, okay? All right, and so that's information that you would maybe not necessarily get from a static structural analysis, okay? All right, so that's a very, very brief introduction to the fatigue tool in ANSYS. And so I will admit there's probably a lot more to this that you can do, okay? But fatigue, material failure, material fatigue is not as much of an area of expertise for me. I only know just kind of the basic definitions, but that's usually enough to do something like this within ANSYS itself. Okay. Okay, and so if this is something you want to incorporate in your final project, this is basically how you would do it. All right, any questions on this fatigue tool here? Okay, all right, so that's all I had planned for today. And so, for the rest of class today, I'm just going to be just answering questions on your project. So there are a couple of people here in person. I'm going to prioritize them first just because they were here in person. So let me go make my rounds first, and then I'll come back to Zoom. So if you're on Zoom and if you have questions on your project, just drop something in the chat for now, and then I will come back to you as soon as I kind of make my way around. Okay, okay, so I'll be right back. Check questions on your project?
Yes. I'm gonna go ahead and pull it up.
Okay.
To be honest, and you can probably notice that like most of even the assignments and all that kind of sort of stuff, I was kind of like I didn't finish.
Mhm.
And it's just I have a lot of OCD stuff, so whatever I do, I go into it too much. Like
Sure.
literally the bike crank one, I didn't turn it in and I did a mesh conversions test on it.
Mhm.
But yeah, so I was thinking for this project, since I didn't get the midterm project in on time, I was thinking maybe I can just expand on that
Mhm.
and just do whatever I pick. If that was okay with you.
I would prefer you do a new geometry for the final project.
The only reason I'm saying that is because I didn't finish, but I put so much work into the research and also figured out how to scale it to the exact CAD model
I see.
that I had.
I see.
And
Which geometry did you pick for the midterm project?
the bearing housing.
Okay.
So basically it was a drive shaft center support bearing. So like I looked through a bunch of ASME documents and stuff like that, but I also had one at home.
Yeah.
One that I changed in the past. I wasn't sure if we were allowed to make our own CAD model, so I just
Yeah.
worked with the one that we had.
Okay. So for your case,
Yeah.
I mean, usually I prefer a fresh geometry, but I think for you, just because you did put a lot of effort into it,
Yeah.
I'm okay with you submitting that same geometry for the final project and just kind of doing the extra things and the extra things that are part of the final project. So yeah, for this case, I'll accept it if you do that.
Yeah, so that's one thing. And then another thing is so all the forces that I applied to that bearing housing, I realized when you talked about like bearing stress, like
Mhm.
I think that might have been the last class.
Yeah.
I was like, oh shoot, I didn't apply it
Yeah,
like in that way.
honestly, the bearing loads, I think it makes a difference,
It
obviously,
is, yeah.
but I don't think it's as big of in fact, that might be something you can investigate in your project. You can apply like a regular load, and then you can apply it as a bearing load instead, and you can see how much of a difference it would make. Because I'm actually curious, because I actually don't know how much of a difference it would make.
Yeah.
And I mean, probably it's problem specific,
Yeah.
but maybe that's something you can investigate as part of your final project too.
Okay.
Yeah.
So basically what I did is like I had four scenarios, one with normal driving, one with like track driving,
Mhm.
and then with two different materials.
Mhm.
I planned to do three, but it ended up being way too much work.
Sure.
But now since I have that down, I was like, maybe I can just add on the dynamic analysis. Because what I basically did is I simulated a static structural, but I applied some logic to get an idea of which one would last longer,
Mhm.
and then which one would also absorb the vibrations better.
Okay.
Because like you can make it stronger, but the thing is that like it also causes like that, the life cycle could be really like good.
Mhm.
But the problem is when you over engineer it, then you have all the other parts in your like drivetrain that will have a reduced life.
Mhm.
So I don't know. But the thing is like I put so much work into it, but I don't know, I overcomplicate things too,
Mhm.
and I just don't get them done. So
I see.
yeah,
Well,
that's my issue.
gotcha. I see. Well, I mean, yeah, I mean, I think it makes sense in this case for you to put that towards the final project, just because you already put in a lot of work
Yeah.
in that. So yeah, but make sure that you get the final project in on
Done,
time,
yeah.
because I don't have a lot of time to grade it.
To grade
so,
it, yeah.
So I
That
want to make
makes
sure
sense.
that I have time for that. But yeah, go ahead and use it just so you can use everything that you've written already for it. And then just the extra stuff you can add on top.
Gotcha.
Yeah.
Okay. I think that's it. That's pretty much it. If I
Okay.
do have questions, that are more technical, I'll just kind of.
Okay. Yeah, so I'll be available over email. I'll be more available because the midterm project was also kind of a busy weekend for me. I know you sent me
Yeah,
that email, but
I was like, there's no way because he's got so many other students too, and I kind of
yeah.
did a lot like late a little bit.
Yeah, so this weekend I should be a bit more free. But try to email me by tomorrow afternoon if you can, if you have questions.
That's
Yeah.
one thing, and then I did do some calculation to figure out like what my grade in the class would be.
Yeah.
To I think I would get a 55 in the class if I did really good on the midterm. So
Hmm.
I'm like, I don't know if I'm gonna pass, but I'm just gonna do the project just because like I mean I'm doing this class because I really like enjoy it.
Hmm.
But yeah, I'm just hoping that the curve, if there is, will kind of get me to that passing
I think
level.
there will be a curve because these exam scores were lower than usual, which I expected because this summer session goes so fast, and so
Yeah,
you guys really only had like just a few days to prepare for the midterm,
yeah.
and so a few people did really well, but I would say the majority of people is below, which is expected. I mean, it's hard to really nail this stuff down really quickly. So
Gotcha.
I think there will be a curve at the end. I just don't know what it's going to be at this point. So, but
Gotcha.
yeah, for now, I would say just do your best on the final project, and then wherever the grades land after that, we'll see from there.
Okay.
Yep.
Yeah, honestly, I added this class, but I was so burnt out from the spring and then I
Yeah.
did another class after that. And then, yeah,
Yeah. It's tough. I'm feeling pretty burnt out too, just because I went straight from spring to summer too. So I can only imagine what you guys are feeling too. So,
yeah.
but yeah, do your best, and then yeah, if you have questions, just let me know.
Okay.
Yeah.
Cool. We'll do that.
I want to say thank you for
Okay. Oh yeah, no problem. I'll see you around. I mean, you're coming back for a fall
and
too.
also advising.
Yeah. Yeah.
Have a summer.
Yeah. You too. All right, Zoom. Who's anyone have questions on the project out of in Zoom here? If not, I'm gonna go get a drink of water and go to the bathroom. Actually, look like me. Go back. Yeah, yeah. So I'll have the exams start of fall, and so if you want to drop by my office and pick it up, you can do that then. Hmm. Do you have questions on your final project?
Sort of. I just want to make sure like the geometry that I'm using
Okay.
is considered.
Sure, yeah.
So
Yeah, the exams are there if you want to pick it up too.
Quick question.
Yeah.
So for that bearing housing, were there students that did like hexahedrons over tetrahedrons?
There was a mix, so some people did TEDs and hexes. It can work both ways. Hexes will be a little bit more challenging because it is a little bit of a complex geometry.
Yeah.
But it'll work fine in TEDs too. So yeah.
Because I did both just to see, and I kind of documented it, but
Okay.
I had like so much trouble with the hexes, but I
Yeah.
was like,
It can be tough on that. Some people got it to work, but I'd say more people did tetrahedrons.
gotcha. Yeah, I'm always curious when I do these things. I'm like, am I doing it right? You know?
There's so many different settings and
Yeah.
things you can do in ANSYS. Yeah, it's
Because I did a mesh convergence test, and the issue was like even though I reached 3%, I started seeing singularities not in the stress stuff, but I was looking at solutions for strain
yeah.
energy, and I saw some singularities, but I was like, okay, the locations are changing, but if the like total like because what was important for me, at least for the project, was the collective, like total strain energy that was absorbed, and not necessarily like a particular like critical value. So for me, I just kind of like I was like, okay, it works out because the numbers are the same. But I was kind of like, I don't know what to do because like I did a really good job of making sure that the mesh and like the small little areas had enough elements.
Yeah.
Even with our cap, like I just hardly got mesh conversions.
Yeah.
So I was kind of like, I'm not really sure what to do there.
Yeah.
So
Mesh convergence is hard just because of the limitations of this software. So 64,000 elements is actually nothing in the grand scheme.
Yeah.
So you can really only do very simple problems. And even the midterm project geometries, I would say, are maybe a bit beyond what the limit can really do.
Okay.
So that's not surprising to me. Because most practical finite element simulations on more complex geometries, you have element counts in the millions, and that's very common. So like everything I do for my own work is always in the millions.
Wow. Is that like a standard package with ANSYS?
So I don't use ANSYS. I use kind of my own research software. I do more fluid stuff actually too.
Gotcha.
But yeah, it's most of the time you read any papers on doing finite elements, their element counts are in the millions. At the very least, like 500, 600,000.
Yeah.
take that or just one simulation.
It depends. If you're running a purely static simulation for like 1,000,000 elements on a desktop computer, maybe a few hours. If you run a dynamic simulations, almost certainly you have to run it on a high performance computing cluster. It's like using like 50, 60 computers at the same time. Yeah, and even that can take like hours to do as well.
Do you see like AI like because originally when I was taking machine design, I kind of looked into it a little bit, and but like sometimes it'll take like 24 to 48 hours to like run a full like and so if the company needs something quick, if the part is relatively the same and they have enough of those parts that they've done, they'll kind of just train AI to give them an idea. But I don't know how like good that stuff is because like the thing is like
I can see AI helping in that sense. I think AI could be very good at giving you like a to put it in a very casual way, like a vibe and how the part is performing. I don't think AI is very good at getting very precise answers. And so if you want to know precisely what the stress is at a particular point, I would trust FEA much more because that's a physics-based model. But if you want to get, and if you have the data to back it up, like you've run simulations on, hundreds of these parts before, I would say that makes it a bit more reliable too.
when is an FEA like kind of required in the industry? Because the thing is like for instance, I did a project in machine design and it was like a little metal bracket, and like the safety factor was like 240. So I'm like, you don't really need FEA for those kind of things,
Yeah.
but what kind of I don't know. Like,
Yeah.
because I'm just thinking about what my workflow would be if, I mean, at a company, they'll tell you if you need to do it, right? But
Right.
I'm like, if I want to design my own parts and build them, do I need the FEA? Like, what do I
Yeah,
don't know.
no, it's a good question. Certain industries will have much tighter tolerances in terms of their safety factor.
Yeah.
So if you look at everything like the aerospace industry, everything is like safety factor 1.1, if
Oh,
that, or something like
yeah,
that, or like
yeah.
it would be like 1.01,
I
because
see.
everything is designed such tight tolerances. And so for something like that, you need
Why do
FEA.
they do that?
Just because otherwise it would be you'd have just a giant lunk of metal in the air. And so
Oh, I see. So it's
So-
significant.
yeah, so you need everything to be super tight. Otherwise, just any weight that you can shave off like an airplane is really significant.
I'm assuming it's not the same for like automotive stuff.
It's not as tight, but even automotive can be very tight as well. Especially if you're designing something like a sports car, like that's very
Yeah.
tightly.
I mean, that stuff like for performance, like, yeah, it makes sense.
Yeah.
Especially like for competition stuff, your life cycle is not going to be, because I mean, there's significant performance gains that you can get.
Right. Yeah, but for a part where you just want to make sure that it's not going to break, and the AI tells you your safety factor is like 15.
Yeah.
I'd say you probably don't need FEA for that.
Because I'm like thinking about it and I'm like, if I want to build like it would make sense for me if I was building a trophy truck, for instance. Like these are like these $1 million trucks, race trucks, but you have to do FEA on the chassis because the chassis has so many different things. It has the vibrations, it has life cycle. You want to make it as light as possible.
Yeah.
A bunch of different things, right? But for like a part that I was doing it on, like the drive shaft center support, I'm like, maybe if they're a bigger company, they do it, but like if you're just designing something, you really need to put that level of detail, and I'm not really sure.
Yeah. I think it depends on maybe how much is writing on that design too. And
Yeah.
so, if it's a part you're just prototyping, yeah, I think AI works great for that. I mean, that's kind of what AI is designed to do is very quick prototyping. But if you're going to say that this design that you're going to be proposing with AI,
Yeah.
it's going to be like a $500 million decision, then let's be a little bit more sure
Yeah.
that the safety factor really is $1 million there.
Yeah, I guess too, when you're selling with large production, then those little things matter too.
Exactly. Yeah. So it's interesting. I think we're definitely still in the phase of like figuring out where all this kind of fits together.
Yeah.
But traditionally, because it actually hasn't even been that long since FEA has become a big part of the industry. Like there's
Yeah.
probably still engineers alive today that wouldn't even touch FEA. Like they would just rather just do pencil and paper calculations.
Yeah.
And so, FEA did not have that much time in the spotlight actually compared to other techniques.
That's the thing. Sometimes it's the hardest thing to do research because like in certain areas there's a lot of new things going on. So it's kind of like it's more of experience. Like you've
Oh,
done
yeah.
it, so you kind of because it's so new, right?
Yeah. It's the wild west in a
Yeah.
lot of ways. Yeah, FEA was like that not too long ago. Yeah, FEA was the wild west for a while, but now FEA is a bit more established. But right as FEA gets established, then here comes AI to kind of disrupt things again. But
Yeah.
I think there's a time and place for both. I think they both can exist, and I think companies are figuring out how to work with that. Oh yeah. So I'll have the exams. I'll probably have in my office for the next 2 or 3 years. Honestly, it'll just be somewhere tucked in my office. But yeah, please pick it up as soon as you can, because otherwise it just becomes cluttered. Some of them are actually at my home, just because I bring them home to grade and forget to bring them back. But then my wife gets mad at me because then it ends up cluttering.
I want to ask, like, how much of like my machine design and kind of things do I need to review? Because like when I first learned it, I was like pretty like I had a good understanding, but the thing is that we learn so many things so quickly, I forget a lot of these things, even when I knew them really well.
Yeah.
And so I'm like going into product development for something that I really have an interest in. Do I just kind of read specific to that and some of those things would just pop up for me, or should I go back?
That's usually how it goes. And so usually, when you go out and you work for a company or you work on a
Yeah.
particular product, you're not going to use everything that you learned in school. But it's useful to keep all of your notes, all of your textbooks, so that if you do need to go back and review or something, then you have that reference. It's professional engineering work is not really retaining everything in your head, because that's impossible. It's more just knowing where to look for the information and having a good foundation to know that, this is where I need to look and this is the information that's reliable. Yeah, I look stuff up all the time too. I have all my old textbook. I have my notes even still from undergrad that I still read.
Sometimes I feel like an imposter. I'm like,
Oh well, it's everyone.
I don't remember this. I'm like, yeah.
I mean, no one's gonna ask you, what the Elvis stiffness matrix for beam is gonna look like in an elevator when you go to your company. That's not important. The important thing is, how to use it and how to hook it up,
Yeah. That was another thing by the way, for our bridge project. When you asked like how we're sizing the elements, I honestly did not know. And it was kind of complicated because for the shell structure on both sides, the thickness was the same as the width as some of those beams. What I read online is that like and some of this stuff is from AI, so I'm like, show me where credible sources or whatever. And this is like the thing, like it's also when you do research, it's a little bit like that. But it basically said that for each one of those beams, like you want it to be at least 3 to 4 times, like have 3 to 4 elements per the width of it. But at the same time, it was saying that if you make the elements too small, meaning that the element is smaller than about 2 to 3 times the thickness of it, the mathematical model will be inaccurate or it'll just crash.
Oh, interesting.
So I was like, how do you kind of intertwine both of those concepts, because the width and the thickness were the same. So I was like, should I have just done beams and like if we wanted to do an accurate kind of thing on it?
That's the first I've heard that. Although everyone kind of has their own kind of rules of thumb for like when to use.
That's what I was like, I'm just gonna
shells, and
ask.
so, I mean, the most systematic way to do it is to do a mesh convergence on both. And see, and I'm sure it's application specific too, because it depends on how much loading and what the constraints are going to be in those cases. But I can see that being a good rule of thumb one way or the other.
I just didn't know like what was a rule of thumb on how I should size it, like based as our first kind of like for when we do mesh convergence, we start somewhere.
Yeah. Usually for mesh convergence, I just use the default mesh, and so whatever ANSYS thinks is the just because it's fast. Because you want whenever you start your mesh convergence, you don't want to start really fine, because then everything else is going to be more expensive after that. So start with something really cheap, even though it may not give you an accurate solution, but you have to start something. So start with something, and the default mesh in ANSYS, and this is one issue it's debatable, but it never gives you a mesh that's adequate enough, but it'll give you something that's fast. And I think that's the mistake that a lot of people make when they're using ANSYS without any training, is that they just mesh just because they see it as a step, but they don't know that they actually have to size the elements.
That's the thing. I'm like, I don't know. Sometimes I'm like in that scenario, it was a little tricky. So I was like, even if I did get it a little bit more accurate or whatever, like if it's like 10%, like it's not a big deal. Like a change in the.
It depends. It depends on the application. So 10% can be a big deal in certain applications. But maybe in others, maybe not so much, right? So in a case where like safety factor is already like 300, 10% is not going to make a big deal. And your part is indestructible. It's not gonna fail. But if you're close to like yielding, your safety factor is like maybe like 1.5, 2, then maybe that 10% will make a big difference. So everything is it depends on the situation. Alicia, do you want me to take a look at your geometry?
Yeah.
Okay. Let me come up.
I was just gonna do actually that extend.
Oh.
Like in a way.
Perfect.
Scooter.
Yeah, looks good.
The midterm project, I got the like materials, so I just want to make sure like I didn't make the same mistake, because I've just been like looking up the kickstand usually made out of?
Yeah, so usually the best for that is, you choose a material and then you justify it. And so, you could say that, this material is very common for these kickstands and then have like a reference for that.
Okay.
Not that a reference is required, a lot of times people just explain it and it's like, oh, that makes sense for this application, but a reference does help.
Okay.
But yeah, no, I think this looks good. Yeah.
Just wanted to quickly show you the kind of distribution that I got for the stress or whatever, to kind of see if like it kind of looks like some of the like what you would expect. Because the thing is that when I was looking at it, I was like, I don't know if this makes sense to me. Basically, I had I'll show you the loads, but just show you so you can see it. Sorry, I put so many pictures. The reason is because like I know I'm gonna forget how I did a lot of stuff. Okay, so I had a force that was like a pressure kind of
Yeah.
going down here, and then I
Uh-huh.
just had one that was there.
Okay.
I was expecting that the forces, like naturally, it makes sense to say that the forces or the stresses are going to be largest near the fixed points.
Yep.
Um, uh, but I was expecting it to be in this direction, given that this force was very large compared to like this one,
Yeah.
like 5 times as much. But the high stresses were in the inside, like on like the edges right here instead of the edges here. So
Just like
something
that, right?
that. Yeah. So I was like, I
Okay.
don't know if that makes sense. Because like there's also more material there
Yeah.
and there's less here.
Yeah.
So like I was like,
That makes sense. I mean, that doesn't not make sense to me because you're applying all the loads here, and then you have kind of a sharp drop off of like, the material is free to deform here.
Yeah.
And all of a sudden there's like a hard stop here because of the fixed support.
I see.
And so because there's such a large gradient in terms of conditions here, then it makes sense that stress and strain would be the highest at that location. So
Okay.
yeah, I wouldn't think twice about that.
These are the singularities that I was talking about. And I just put it in the meshing section. Like I would get like stuff like this,
Oh, I see.
and then it would be a different location, like it was here before.
Oh, I see. I see.
Yeah.
But those are pretty small anyway too, right?
Yeah.
Yeah. I would say that that's okay. You always have, so there's a thing in
Because like this one is like I think it's like the value is like this one's like twice as large.
yeah.
So but the thing is like I was looking at collective strain energy from the little table that it gives you.
I see.
So I was like, it doesn't really matter too much, but I was like, yeah, I was like, if you were just looking at where the strain energy would be highest, like how would I? Because I reached mesh conversions,
Right.
and I was like, dude, this mesh, like, if you look close, like this was how it was originally,
Yeah.
and I was like, I'm gonna make the mesh even smaller, like, because there's 2 elements here,
Yeah.
and then there's like 2 over here, and there's 1 over here. I
Yeah,
make
yeah.
it like 3 or 4 here.
Yeah.
Like you can kind of see that there.
Yeah.
Just to see, and yeah.
So these are common to have, some defects kind of near the edges. So there's always going to be what's called edge effects. When you have just like a sharp, like that's essentially a sharp edge of your geometry. So that tends to happen. So that's not surprising to me. But also this is not. Yeah, I wouldn't worry too much about that because if you've already shown that your mesh is already converged,
Yeah.
then something like this is probably honestly just like that looks like material precision or machine precision, right? It's something 10 to the -8. And so that's yeah. I would say you did this looks like a good mesh to me. It looks like you did a good job.
Okay. Cool. Yeah, just feel free to like, I know that you have to grade like a lot of people's,
Yeah.
but if you want to grill me as hard as you can, like that's cool with me.
Okay.
Yeah. Yeah.
No, I'll grade everyone the same. That's how it should work.
Yeah, I don't know. I just want to know like, did I do right? Like,
Okay.
Yeah.
I'll give you feedback. I think that's
Yeah.
probably what you're looking for. Yeah, I'll leave comments on your rubric to, yeah, give feedback. Usually I don't for the final project just because it's the final project.
Yeah.
But when I grade you, I'll make sure I'll give you comments and feedback.
Oh, okay, thank you. Sometimes like I have like when you really want to do a good job, it's like I gotta do it. Like you know what I'm saying? But then when I get in the mode and I start doing it, but then like I just can't stop like the level of detail, and I'm like, dude, I gotta stop somewhere. Yeah.
Yeah, yeah. My wife has a similar, so my wife's a designer, very, very different field, but you
Yeah.
know, with design, you know, there's Pandora's box. Like there's always improvements you can always do to design.
Yeah.
And so my wife kind of struggled with that for a while because you know there's always something you could always improve with like whatever she's designing. But yeah, but there's deadlines and there's kind of more real world
Yeah.
stuff that you have to kind of turn in at some point too. So it's a struggle, and I get it. But yeah.
Yeah. Yeah. It's kind of my school struggle. I get stuck in this stuff, you know?
I see.
Yeah. I think I'll call it a day. Take a break and get back on it.
Sounds good.
So, the validation calculation, please, for the new unit, or was it supposed to? No.
Oh, I just did that as an example.
Okay,
So,
okay, because I was
yeah.
looking through the notes and I was like, I don't remember this.
Oh yeah. I know some professors do it in solid mechanics, some don't.
Okay,
I just use that as an example, but probably your validation calculation would be anything basically. So yeah, I just had that as an example.
Normally, like in a full-length class, do you kind of require like fatigue as a like a assignment?
No, so the only ANSYS activities are the 6 that we did together. The only difference is that in a regular semester, I have students turn in all of them for credit. But because this is the summer, 5 and 6 I just did for fun basically. And then the rest of the handouts are just handouts, and so you guys basically got the full experience. The only difference is that 5 and 6 were just optional activities. Yeah, usually for the regular semester, the last week is like this. Actually, I just have open office hours for people. Yeah.
What's your kind of like favorite like class to teach?
That's a good question. I don't really have one that I hate. I mean, they're all just different subjects, and so I kind of treat them all the same. Um, yeah, I don't know. They're all fine.
Honestly, like I love machine design stuff. This class is cool. Manufacturing is cool. I don't know. I'm like into like all of that stuff.
Yeah. No, that's good. It's good.
Fluids, like I to be honest, like I wish I had learned a little bit more in that class. But I don't know. I had a tough time visualizing some of the things.
Fluids is hard because it is really hard to visualize because it's so different than anything that you've done before that. I would say like everything like statics, dynamics, machine design, solid, all that kind of builds on each other.
Yeah.
And it's like all of a sudden here's fluid and it's a completely different thing. So it's a struggle for everyone that takes it.
I kind of like thermal, like I did well in thermal. The thing was like I just I didn't because like a lot of the stuff that we learned is like in cycles that we don't see. Like even when it comes to like combustion and engines and stuff like that. I was like, you'll see this in power plants and stuff like that.
Yeah.
But just like
You don't walk into a power plant just to just to browse around. Yeah.
Yeah, I was like, I've never seen this.
Yeah. Yeah, that thermal fluids is hard to visualize a lot in general because of that. Heat transfer, I think, is a little bit easier to visualize. You can see some of that in your daily life a bit more easily. You can feel temperature. I think that's what helps with it. But yeah, fluids, thermo, it's difficult for that reason. It's hard to see those things in reality.
Definitely, man. All right. All right, Professor. Take care.
Too.
Same work.
No. I'm contractually obligated to be here till 5:50, and everyone on Zoom is here anyway too. So yeah, don't worry.
Okay, thank you.
Because in a regular semester too, most people, not everyone has access to ANSYS on their own personal machines, so they have to come here to do the work. So someone emailed and said they're coming back at 4:45.
Oh.
Yeah.
Professor?
Steve, I hear your mic going, but I don't think I have audio right now.
Okay.
Oh, yeah. Okay, there you go. Now it's working.
Okay. I just had a question about the validation process because I was doing the math required to find the total deformation equivalent stress.
Yeah.
The numbers are not the same as ANSYS at all. They're
Yeah,
like,
that's normal because yeah, no matter because usually you're doing something in ANSYS that's a lot more complicated than your validation. That's okay. You know, I don't expect people to get matching on the validation, but I still want you guys to go through it because it is an important part of finite elements. It's just within the context of this class, it's hard to do a really good validation study or validation measurements. So that's kind of the best that we can do under the constraints. And so I want you guys to do it and report it, but yeah, I'm not grading you on whether it matches or not. I'm
okay,
just,
so even if it's like really far off, can I just, would it, in my report, do I just explain like, I guess my limitations in my validation process?
yeah.
Okay. All right. Thank you.
Yes, especially for your case, I'm thinking to your case. I think it would be hard to get good matching in that case. So
No,
yeah,
it
don't worry
it,
about it.
it it is because I was looking in my machine design textbook, specifically the bearing section,
Yeah,
and the closest thing I can find to like what I'm doing is the Hertz contact
yeah,
equation.
yeah,
But
yeah.
for that, I need to find all these different things, and then I need to find the manufacturing specifications of the bearing, and I'm like, I don't know, I just designed it from what my professor gave me. So
Yeah, no, I expect it's going to be hard, and even in ANSYS, there's a lot of assumptions that we're making too,
yeah.
and even if you do find an equation for like a ball bearing, it's not going to have those same assumptions, and so yeah, it's always hard. It's hard to find a good validation calculation, but just do the best you can, just report it and report kind of the assumptions, and that's mostly what I'm looking for.
Okay, thank you.
Yeah. Hey, Wheel. Is your mic working?
Yeah, Professor, sorry.
Yeah, I saw your email. I think that looks fine. Um, you're planning to do kind of an interesting material for it, right?
What was that again?
You're planning to do like a non-standard material for that geometry, right? I looked at the
So,
figure.
yeah, so I was gonna, well, the first one I was gonna do it was stainless steel,
Okay,
304 stainless steel. The other material I was thinking it was FDM, 3D material,
okay.
or we could do Delrin, if possible. Like
What
it's
is that?
aluminum. That's aluminum, like I guess with like a finish, you could say like a coating finish.
Okay. I'd be
I don't know.
interested. I'd be interested in the FDM. I think so the geometry is a little bit on the simpler side, but I think if you were to do it with like a like a non-standard material, I think that'd be interesting for your final project.
But you said that it was gonna be a little bit harder, right, on the analysis part. Like, I don't know if you meant the meshing or
So I'd be interested in the material. So like choosing like a non-standard material. So let me go ahead and share my screen now just so you can see.
Okay.
So if you go to the page for week 5, part 3, you'll see that there's a lot of these handouts here for different niche features in ANSYS. So
Okay.
for like a 3D printed material like FEM, I think probably you would want to prescribe it as an anisotropic material. Um, so I would look at this handout and see if you can apply that a material like basically different material properties in different directions. So it was a while ago, but I think maybe second week we talked about material properties. So this is where you would do something like that.
And then the material properties, I would just probably there in the website, right? I just gotta look for them.
Yeah, yeah. So you'd have to look it up and see. Yeah.
Okay. And then as far as to like the loadings,
Mhm.
I don't know if you saw the sketching that I had.
Yeah, yeah. Let me bring it up actually again. Let me not share my screen. Okay. Okay. All right. So it looks like, for the most part, you're going to be supplying a tensile load to this. So
Yeah.
load up that way and load going down that way. So I think that works for one of your loading scenarios. Um, you do have this kind of part up here with kind of a lip. And so whenever I see something like that, you can think of maybe like a torsional load. So maybe a load that's kind of twisting up there and kind of seeing how that torsion propagates through the structure. Because what torsion is going to do is that it's going to induce shear stresses in the model, and you may get some shear failure in that case. Because for a part like this, tension and compression probably is not going to cause that much stress. Honestly, you probably have to do a lot of tension in order to get a good amount of stress. But if you do torsion, you're going to get a lot of shear stress, which will fail faster than tension or compression.
So that on the top, it's a clip. Basically, it's a pin that to connect to the instrument.
Oh, I see.
So to we could still apply like torsion, you mean, on that clip right there, on that
Exactly.
pin?
Yes. Yeah. So
Okay.
is the clip fully attached to the part here? Because I see it up here, but not on the isometric view.
Oh yeah. Yeah, no, it's not. It's just a hollow hole, so where the pin gets inserted
Oh, I see. I see. Okay. Okay.
to yeah to clip it on. Well, to basically fix
Oh,
it to the instrument jaws.
oh, I see. So this part really only experiences tension forces. It doesn't really experience anything else, huh?
Yeah, I don't know if speed affects it as well, because we would be pulling at a certain speed.
Oh, I see. That would be a
So the
little bit
top
hard.
air,
Yeah, yeah. Go ahead.
so the top part, like basically that arrow point is basically me saying like, hey, this is gonna be going upwards at a certain speed, and then at the bottom where the circle is, let's say there's the component that we're testing, we're trying to do the test on.
Yeah,
Basically, that's where that part is gonna be holding on to that fixture. And I
I
guess,
see.
that component is going to be it's going to be trying to prevent that fixture from going upwards.
I see. I see. Okay. Hmm.
So basically, like uh, what I'm interested in is if that bottom portion plate of the fixture, would it would it not fail during the test?
I see. I see. I see. Okay. Hmm.
So the speed, it's not considered like a loading, right? Or
Well, so the speed would you could translate that into a force. Basically, you would do like almost like an impact situation where um, when so the speed itself doesn't cause doesn't cause extra force, but the acceleration does. And so if you're starting from scratch, like you're starting from complete rest, and then you suddenly move it upwards with a certain acceleration, like you can compute kind of a like a dynamic force in that case, based on the amount of acceleration that it's experiencing. So you can do that, and so you could vary the force, and then you can translate that into like an acceleration, like the max acceleration that it could handle before it breaks. Um, I think that would be good. Um, let's see what else.
so then that would be one load, and then the the load experiencing at the bottom, that could be a second one,
Well, I
or
mean
would
that
that
would
all be
be
considered?
so we're looking for two different loading scenarios, so different ways to kind of configure the boundary conditions, right? So one would be kind of the tensile load, and so one way to do the tensile load would be to do it based on the acceleration that we kind of just computed. Um,
Okay.
and another boundary condition situation. Um,
I know you mentioned something about thermal yesterday.
you could do that. You could do a thermal simulation. Um, you could do a modal situation simulation as well. See what else we have available. Um, you could do fatigue life analysis. I think that would be interesting, just because this part's going to be used over and over again, I'm guessing, right?
Yes. Yeah, it would be.
So you could do
Yes,
fatigue.
actually, that's good. That's a
Yeah,
good
so,
idea.
so I would look at this handout. So this is handout A4. So unfortunately, fatigue life, we are limited to certain materials, so they have to have this what's called the SN curve. So I know structural steel will have it. We just saw today aluminum alloy has that SN curve as well. So I think this would be a good analysis you can do on for your project as well. Yeah. This could be like your second loading scenarios. You can do a fatigue life.
Okay, got it. You still gonna have office hours tomorrow?
I don't have office hours tomorrow, but I will be available for email. And so
Oh, that's right. Sorry, that's today's Thursday. I thought
yeah,
tomorrow was
yeah.
Tuesday.
But if you did want to set up a Zoom meeting tomorrow, just send me an email. I'll see if I'm available, and we can try to meet. I'll find a time to meet tomorrow.
Okay, sounds good. Yeah, by tomorrow I should have everything ready
Okay.
with the design and the analysis and uh, more like of a review, see if I did the
Okay.
boundary conditions right and all the analysis
Okay.
part.
Yeah. So yeah, go ahead and check out handout A4. I think that would be a good one for you to do for.
A4, that's for the fatigue, right? A4.
Exactly. Yeah. Yeah.
Okay. All right, sounds good. All right, thank you.
Yep.
Sorry. Until what time are you gonna be here?
I'll be here till 5:50, so at the end of the standard lecture time.
5:50. Okay. All right. Probably hopefully it gives you enough time to start it and maybe you could take a look at it. All right,
Okay.
thank you.
Yep.
Present.
What's up?
I had a question on I'm doing the rotor right now.
Yep.
I tried applying a convection and a heat flow to the geometry,
Okay.
and it was giving me errors that wouldn't let me run. So I switched it to a temperature uh a temperature condition,
Yep.
and that let me run it. But is temperature really like is it still valid? Because I don't know if it's more real world to put a heat flow on there.
So you need at least one temperature boundary condition because that kind of sets your that's your constraint basically. So it's just like a structural simulation. You need at least one fixed support in order for the simulation to run. Thermal simulations, you need at least one temperature.
Oh,
Uh,
okay, okay.
yeah, so I would so for your case, I agree. I think, for the most part, you want to have convection and heat flux. You do need to set like a reference temperature somewhere. So maybe like where a good place to put it would be maybe near the center of the brake rotor, because usually that's usually not a place of interest, I would say. So you can kind of set that to be maybe ambient temperature, like maybe temperature of like outside or something like that, just like normal outside temperature. And then yeah, you can apply heat flux and convection from there. Yeah.
Okay, I'm gonna try that right now.
Yeah.
Professor.
What's up?
Alright, so yeah, I applied it, everything worked.
Yeah.
Do you have any requirements for what I need to present on terms of the result analysis?
Oh, for the thermal analysis? Oh, that's a good
Yeah.
question. Definitely the temperature. Um, I would be, I was gonna say the heat flux, but if it's something that you're kind of prescribing, then maybe it's not as interesting. So I would say definitely the temperature. That's usually the main output for a for thermal simulation. And then you can comment on the temperature because you can see pretty easily to see if your part's going to melt or not. See if the temperature is up to that melting temperature. And a lot of things, actually a lot of things on a part is dependent on temperature, like things like its density and its material stiffness as well often shape the temperature as well. So I would say at the very least temperature. And then yeah, let's go with that.
Okay. And then just to make sure on the graduate portion,
Uh,
all you need in terms of deliverables is the boundary condition justification, um, the harmonic graph, and then the modal table.
yep.
We don't gotta do anything else on terms of like what we did for the undergrad portion, like the validation calculation or
Nope.
no
I mean,
background or nothing.
I do expect you to explain the results a bit, and so it's not just the figures, and so you definitely want to discuss it and describe it in the text, especially in the discussion. So kind of talking about why that's important. But yeah, you don't need to do like a separate mesh convergence or discuss the boundary conditions or anything like that because that's all. A lot of that should be the same as your standard your standard configurations.
Okay. And then one last question real quick for the mesh conversions, since I'm doing two different geometries, I gotta do one for uh
Yes.
each geometry.
Yes. Yeah.
Okay. Sounds good. Thank you, Professor.
Yeah. No problem. I believe you have your hand raised.
Yes. So I already created the model in SolidWorks. What file does ANSYS accept?
So usually the best one is either IGS or STEP, STEP. Yeah,
Oh,
either.
step. Okay. There's step AP 203 and 214. Either one is fine.
Either one should work. Yeah.
Okay.
Yeah.
Classes next semester?
Yeah, so I'm teaching fluids, 333 and 410 again,
Okay.
and then a graduate level fluids course, 520.
Senior design.
No.
Oh. Thank you.
Yeah, no problem. All right, it's 5:50, guys. So I'm gonna head out. So if you guys have any final questions on the project, I will be available tomorrow. I'll try to be responsive on emails over the weekend, but no promises. And so if you have questions, try to get them to me by tomorrow afternoon so I can get you an answer. Thank you guys for being here for the summer. I know it went really fast, but I appreciate you guys' hard work. And yeah, looking forward to see you guys' final project. So I will see you guys around, and I'll be here in the fall. So I know a lot of you guys are doing senior design, so I'm sure I'll be seeing you guys around, especially in advising. So have a good one, guys.
Thank you, Professor.
Thank you.
Thanks, guys.